Alright, time for another draftphysics.com video presentation. So we have some comments on the lever launch preview video. Okay, so I guess I should say something like, maybe this is just part of the show. Again, why did he post this, not very useful video in the sense that it's clearly not the experiment I've been describing. And he has the flaw in it. He admits the flaw is in it in the video. He admits the lever's bending too much. So what's what exactly is the point of providing this piece of deception, frankly? Because the results will be very different when he uses a lever that doesn't bend. It's just going to be a fact. Very different. But anyway, so let's do some of these comments. I want to get to the mindless one last, just because it's it's just such a change of pace for mindless marbles, just so out of character. It's actually a well thought out comment, kind of amazing, and then you can just oppose that to this Ian Gosling piece of crap. So very good job. Nothing wrong enough to give an erroneous result. So even though physics Michael says right in the video, the lever's bending too much, it's not an inelastic. Okay, it's not elastic. Again, this stupid word elastic and inelastic doesn't. You can't use. You have to use super elastic for when it stores energy. So anything rubbery, you have to say super elastic, because frankly, rigid can produce. Can conserve momentum. Nothing's deformed permanently, and you get a reflection. You get all of your momentum back. So the word elastic really doesn't work, because springs and something that doesn't have a spring and is very hard will produce the same outcome, like in a Newton's cradle. You can do a Newton's cradle with a spring, okay? Same mass, no spring, metal against metal, and it works. Put a spring in, and it still works. It still does exactly the same thing. Depending on the spring, though, I would imagine. So if you have a spring that compresses slowly, you probably can get a reflection, and break the Newton's cradle. But anyway, bendy lever, so he puts that in quote, being a typical response from the excuse finder. So even Brozo conceded when he made his first lever 2 years ago, he acknowledged that when he used a piece of wood, it bent, and he replaced it with a piece of aluminum. So it's a real thing, okay? And again, the science defender is mocking clear defects in an experiment. I mean, they're just clear defects, clearly things you don't want the experiment to be doing. Okay, everybody agrees it's not exactly what you want to have happen, and here he is mocking it. But no, that's fine. That's the way experiments should have defects in them. That's the way you want the experiment done, is the way you didn't expect it to be. You don't establish criteria for the experiment, and then if you don't meet the criteria, that's fine. That makes the experiment even more fun. Anyway. Draft will never accept results no matter what you do, Michael. So this is coming from the guy who hid the results of his Play-Doh experiment. So his Play-Doh experiment got exactly results consistent with what I stated would happen, exactly as I predicted, and he didn't publish it. He says he didn't video it. Why wouldn't he video it? He videoed all the other experiments. Why wouldn't he video the clay one? Why wouldn't he set it up and videotape it? Why wouldn't that have happened? Okay, no, he chose not to show it. That's the simple truth. Okay, because it isn't consistent with what he wants to prove. And that's what he's demonstrated, that he'll do the experiment in any kind of eccentric, silly way. And as long as he can get the results, bend them his way, he'll publish. And when they don't come out his way, he don't publish. So it's the same thing Brozo has done. Brozo's done hundreds of experiments we never get to see, because they didn't come out the way he wanted them to. And that's the simple answer. And that's how dishonest these pieces of shit are. So Dispar, playing the middle of the road here. Thank you so much for taking the time and effort to put up this setup. It's clearly not very good. Your work is deeply appreciated. Well, by you maybe. So far, I'm not too convinced his motivations are as clean as they should be. Because again, why would you publish this half experiment? I mean, it's really not up to snuff. Why would you publish it? All right. It would be great to see, like others have suggested, what the outcomes will be with a more solid lever. And there are other defects, frankly, to point out, which Mindless Marbles, again, to my surprise, points out in a very concise manner. He goes right through the list. All right, is it perhaps possible to use a steel rod or something more rigid? So he could use, I think, the flat, you could even use a flat plastic, for example, ruler. Something that's wider than it is thick. You just have to prevent it from twisting, because then it can't bend, in the thick dimension. So if you hit things, and it's also going to hit on a very small point, which is also good. So that's probably going to make the better transfer device, you could call it. I'm also thinking that to minimize collision time, we would have to use small but rigid contact points. So this is something I saw and I didn't mention, but in the video you can see, let me see if you can see that. Yeah, you can see it. All right, let me go to an image of the other cart. You can sort of see the cart there, but let's get a better image of the cart there. All right, so right here you can see, I guess I could make that bigger for the sake of the argument. I need to do this and this. Move this over there. All right, so in this image you can see this little rubber. He has like a little something that is flexible and then a piece of Velcro on it. Okay, and yeah, ideally this should just be something rigid. It's better to have a small contact point, to have it so the lever doesn't rub against the big surface. It only rubs against the small surface is the ideal, because the lever isn't going to, the contact isn't going to be straight in this direction. The lever is going to hit this way, so the cart and that surface is going to rub a little bit. So you want to minimize that and not have it hit the flat surface of the cart. Now when you put the other cart on the lever, you put it against the flat surface, which wasn't frankly ideal, because it's sort of, okay. I mean, obviously the edge of the lever will do the pushing, so it's not too bad, but I mean, again, they're not identical. They really should be in the same configuration and have the same contact with the lever. Yeah, because that's essentially what you're trying to do, is transfer the energy, and there shouldn't be anything in the way of this even and good transfer. So that is a downside. I don't think it's really necessary to protect the cart or any of the other logic he's used to say that he needs to justify any kind of rubbery device between the cart and the thing you're hitting. You want the energy to go straight in as quickly as possible, sort of as Mindless Marbles has stated, which again is surprising. The other point is that he doesn't have to use this whole lever, so you can clearly see he used the whole length of the lever, which you really didn't have to do. So I mean, he could have this 5 inches closer, and then you could have this 10 inches closer, and you'd have less bending then, and so less of a problem. Now obviously the longer you make the lever, the easier it is to see all of the action, so that's kind of nice. But clearly the length is also a downside in terms of you have to move more lever, and the bending problem shows up. So to get rid of the bending problem, probably best not to do a lever any longer than you really need. So just go with a length of lever that's necessary to separate the two carts, and not much more. All right, continuing. So I'll pause and fix this. Alright, so let's see what else Mindless said. I'm also thinking to minimize collision time, it would have to use a small but rigid contact points, like in a Newton's cradle. So in the Newton's cradle, it's steel ball against steel ball, and it's the edge of the steel ball against the edge of the steel ball. The coefficient of restitution, okay, so that's just the coefficient of what the vibration time. should be 95%. So I said if you got 90%, you're doing okay. So if you conserve 90% of the momentum, you're doing, we have an experiment. We have some realistic hope of, getting really results that are definitive. But the time for the collision should take place almost instantaneously. That is, you have to have a mechanism where there isn't some springy thing that absorbs the energy, takes time to do that, and then takes time to release it. That delay means that the energy is not going to get into the object. It's going to be a waste of energy. Because by the time the spring re-expands, the object's already left. So it's going to be just wasted energy. Let's see, I'm not sure how feasible this is. Well, that sounds pretty feasible. I mean, using something better than a bending piece of wood seems pretty easy. But it would be helpful. So at least it's a nice, clear statement about how the real experiment is to make all of this very rigid, so there is no delay in the transfer between the momentum on one side of the experiment and the momentum on the other side, and such. So the Sean Walker replied to himself with, "Exactly as I predicted," and then the bottom line is V2 equals V1. So obviously that didn't come out as it didn't happen. V2 does not equal V1. So the velocities obviously don't match. But anyway, no point talking to the retard. The free energy nut, as Self pretty much described. All right. So I guess I could point out that, because of apparently this experiment isn't as easy as it should be. Okay, I guess I should point out that there are other experiments that will do the same thing and maybe do it easier. So I guess it's worth just noting that again, as I did in the previous video. I guess we can get rid of that. So yeah, maybe the spring type thing, or the catapult. But there's different ways you can do it, I was thinking, and we could go back to the whole gear argument. That really, that's all this is about. Is we should be able to concede a point, about weight and fulcrums, and that if I have a 2 mass here, it's going to weigh the same as a 1 mass out here. So those two things, if I just had the 1 mass, okay, it's going to provide a certain amount of resistance here. It'll take a certain amount of energy to move it this arc, okay, that much distance. All right. And that if I took the 1 mass off and I put the 2 mass on, it's going to take exactly the same amount of energy to get it to this position, okay? Same thing. That theoretically moving it all the way to this 90-degree point would be identical. I couldn't tell the difference. If I put a 1 mass here and a 2 mass here, I couldn't tell the difference between those motions. That they would feel exactly the same. So if I tied a weight to this end and just dropped it, okay, or I could put a spring on here and I could compress it, okay, and then fling the objects. So there's different ways you could do it. And all you're really saying that is theoretically it's got to be the same weight. This weighs exactly what this weighs. And so you're basically flinging the same weight through the whole process. You're moving a half mass at twice the velocity as you're moving the other mass. And so theoretically these should fly off of here, with this being twice the velocity of this. And I don't see any way to doubt that. I don't see anybody drawing a picture of how this is actually heavier somehow and it doesn't go twice the velocity, and somehow you can tell the difference and all of that stuff. There's no logic or reasoning that they balance perfectly. Okay, that is, I can put this on this side of the lever here and it'll balance that perfectly. So we know that they're applying the same pressure. That when this is over here, if I put the 2 mass right over here and take it away from here, it balances this perfectly. So it's obviously putting the same pressure against motion. and they weigh the same. So I mean, just saying, technically that weighs the same. I can't see how the outcome's going to be any different than what I just stated. So there are different ways to do the experiment. Some kind of catapult. I mean, technically you would call this a trebuchet. You know, you're just going to put a weight over here. It's going to have a known amount of force being applied to it by gravity, and you can't change that. There's nothing's rubbing against it. All you have is this string, and so the string is going to push its whatever change in its velocity, that is its free fall speed, will be changed, because it's not going to fall as fast, because the energy has to be used to move these objects. But because they weigh the same, it's going to affect this exactly the same. So this will move exactly the same. Whether I have a 2 mass here or a 1 mass here, this is going to do exactly the same thing. It's going to fall and rotate a little bit. But yeah, the spring thing works. I mean, Brozo did that experiment, got almost a 2-to-1 relationship, so I've already talked about that. I mean, it's a pretty close to, wow, yes, shows you the result. This goes half the speed that this goes. So it's already done the job that needed to get done, which was, it's proven the fact. And then again, Gosling did the experiment just dropping weights on a clump of clay, you know, a little cylinder of clay, and he got the 2-to-1, you know, drop the half mass from 4 times the distance, and you get the same amount of compression in the clay. 2 mass here, 1 mass here, 4 times the distance, same amount of energy applied to the Play-Doh. Alright, proving kinetic energy is not relevant. 1/2 mv squared is not a real thing that happens. Now, I just was watching some more videos on linear motion and kinetic energy, and what else do they call it? They call it some other thing. But anyway, and yeah, they're all deriving how many joules it is, but none of them do they measure the watts, you know, measure the joules, measure the actual energy. So they all just make a statement about how much energy gravity applied to bend the satellites, and they just say something like 2,500 joules. No one measured it. There's no, it's never proven. It's just some statement made that this is what our math says the truth is, which isn't any better than me saying, here's my drawing of a lever. Aren't you convinced? Now, I could argue that I did show the lever oscillating perfectly, okay? So I did give it some energy, and it oscillates, and the nature of an oscillator is, you know, I think as most people understand an oscillator, is that all the energy goes from one side to the other side. So for it to oscillate, it has to be the same amount of energy on this side as there is on this side. So I mean, I have the half mass, twice the distance, and I have the full mass, 1 unit of distance, and it oscillates perfectly with twice the kinetic energy on one side and half the kinetic energy on the other side. Doesn't make much sense, right? So there are already experiments indicating the truth, and you know, what we're seeking is something that's really going to confirm that truth, frankly. And we're going to have to keep waiting on it. So there's some other experiment, I can't remember what it was. But we could talk about the cylinder thing, hydraulics, all of that stuff, which pretty much proves the case also. But anyway, we'll get to that eventually. So I think I'll just pause here, and we'll see if we get any new comments, and see if we can make more of a video here. Or I can talk about some other experiment that I just didn't remember, but you know, I'll just wait and see if I remember. Alright, some hours later, no new comments really, not much anyway. So one other guy, Basin Bass or whatever, I do think the lever should be less elastic material, like metal pipe of some sort. So again, this word elastic is just such a misnomer. It's such a mess. It's just useless in a sense, because most people are saying elastic when they mean something, I guess, something stretchable or bendable, but really elastic means steel ball. So, it just doesn't work. There has to be a distinction between hard elastic and something that's rubber, that stores energy and then releases it again, versus clay or, something that deforms permanently. I mean, deforming permanently should maybe be the only thing that's called inelastic, and everything else should be elastic, I guess. Something like that, anyway. Okay, so I think that's it. So no responses. So mindless marbles 21 hours ago. So nothing to report. Commercials on the video now, which is a little bit disappointing also, but whatever. And such. So I guess I'll just sum up with points I think worth making. I've probably made it before, and I'll just make it over again. But all of this is about is it doesn't make any sense to have these two definitions of energy, momentum and kinetic energy. I think a reasonable person could say a duality is kind of nonsense. This is sort of like wave-particle. It's really not a wavicle or, whatever. Some bastardization of the two. It's probably one or the other. In this case, momentum does work. It didn't need to be fixed. Leibniz showed up and just wanted to be different, and that's pretty much all there is here. He didn't fix anything. You can almost argue that it's like Einstein's relativity theory. Didn't fix anything. Didn't explain gravity. Didn't explain anything. It just provided a pretty lame, in my opinion, excuse for the existence of a force, but it didn't explain what the force did. So the simple experiment that has been illustrated over and over, I've talked about it anyway. It was, you're just combining. Let's just say, and we'll do it this better way. Okay. You have a one mass vehicle. You're moving it at a velocity. One velocity. Well, let's just say 2 for the fun of it. Alright, so it's going 2 velocity and it's a 1 mass, and then I'm going to drop another hunk of the same mass on top of it, and it will become, a 2 mass. And the fact is, it will go 1 velocity. Okay. So this is what it's going to equal. This is what's going to happen. And it makes perfect good sense. You end up conserving the momentum. And the excuse is, you lost 1/2 of this 1/2 mv squared. If you use that formula, this has twice as much energy as your outcome. And they make excuses like there was a bunch of sparks or sounds or all kinds of other stuff, and you can sort of understand, especially when the experiment's done this way, dropping the weight, that all the force that combines the two objects is basically provided by gravity. So it isn't stealing any of its energy, because you're basically adding energy to the system. And even though you're adding energy, you still don't end up with any extra here. But of course, all that energy is in this direction. It's not in that direction. But anyway, it's the bonding force. So you're not paying for bonding the two objects together. So you can understand that any sound you make comes from the gravity. Any dents or any friction is coming from the gravity's force. You're not using the motion this way to do anything. The simple argument is you have to know that, there should be some way you can do the experiment where you don't lose half the energy. But the fact is, if you do the experiment without losing half the energy, then you have to make free momentum. And that clearly can't make much sense to anybody. So, the simple explanation is there's no such thing. This is just a figment. Okay, this doesn't have any, this is the reality, the MV at the core. That's all you need. You can understand that the gun bullet thing, the bullet doesn't have 2,000 joules of energy, and the gun recoil is only 2. It's momentum. They have the same momentum. And it's just that the energy's in a different form. This is lighter, one atom going 1,000 miles an hour, and this is 1,000 atoms going 1 mile an hour. Come on, it's not that hard to understand that the two forces are the same and that they'll dent things a little bit differently. The speeding bullet will make a very good hole in a door, and the 1,000 people pushing will push the door down. So yes, the application of the force might be different, but the force itself is the same. So that's what this is all about. This lever experiment is just a way of trying to demonstrate that yes, you can in fact do this experiment in reverse. You can take the 10-ton train going 5 miles an hour that has 1/2 the kinetic energy, and you can make a 5-ton train going 10 miles an hour out of it. And that basically will prove that kinetic energy is a fraud, because it's just obvious free energy. And simple things like levers can't make free energy. I can't put the 10-ton going 5 in this side, get the 5-ton going 10 out this side, that easily make free energy, free kinetic energy. Obviously the momentum will be conserved. So this experiment, again, in all the renditions of it so far, it's not that complicated. You're just saying, I want to try to conserve the momentum. I want to take the momentum in here, and I want it to come out on this side. And I don't want any reflections. I don't want any not conversions. I want to take this, make it use all of its energy, put all of its energy into this object, and see what it happens. And obviously if I can do that, I'll conserve the momentum, and I'll make twice as much kinetic energy, and basically prove that kinetic energy isn't a real thing. Alright. So I just don't understand why people can be so confident that kinetic energy is a real thing when so many observations aren't consistent with it. So many things don't make any sense. Does it really make sense to you that it takes that it takes 25 times the fuel to go 5 times as fast? Or that if I went 5 times as fast, I'm going to do 25 times the damage? Isn't 5 times the damage enough? Come on. Twice the speed, twice the damage. Not 4 times the damage. 3 times the speed, 3 times the damage. Not 9 times the damage. Come on. Yeah. I really shouldn't have to make this argument to intelligent people. They should just see some of these experiments and these lame excuses. You combine 2 objects, you create a third object, twice the mass, going half the velocity, and you make up some excuses that somehow it lost half the energy by making a whole bunch of sparks or moving things or making sound, but it didn't use any momentum. So it moved little pieces, it broke pieces off, it did all kinds of stuff, but it didn't use any momentum to do it. You have all the momentum in the other object, and yet you're saying half the energy got lost doing a bunch of work. So you did work without using something's momentum? Come on. You can't think that's great theory. You have to have a little pause. Come on. Some sense of maybe, yeah, that does sound a little weird. That doesn't sound quite right. It's got to be something inside of you that says, oh, I really probably shouldn't, I shouldn't bet the house on this. Come on. Anyway. Alright, so I guess that's enough of a video. Can't do much else. We'll just wait and see where this goes. Again, I'm not going to assume that Physics Michael's playing games, but it does seem like he did this pre-video, which seemed unnecessary. Where he was talking about his predictions again, and then he did this video, which is doesn't show anything close to the experiment I've described over and over and over again, and you just gotta wonder, is this just the game that's going to be played or what? But anyway, we'll see. So till the next time and such. I think that's it. Yeah, that's it. All right. Till the next time and such.